very much. So yeah, there's the title, Specifications and Theorem-Proving at ARM. I didn't actually come up with that title. It was suddenly magically created for me, but it's a good title, so I'm happy with it. I'll start with some introductions. So I'm Anthony Fox. Obviously, I'm quite familiar to a few people because I was at the Cambridge Computer Lab. I started working there as a postdoc with Mike Gordon in the days when Peter was still doing TCP/IP specifications and work there. And I joined ARM Research in 2018, so getting on for 6 years now. And I'm now part of Jad's team there in the group called ATG, the Architecture and Technology Group. And we've recently been joined by two people who also have a sort of similar-ish background insofar as they do theorem proving. So we've got Hrutvik, who many of you might have met. He's in the audience over there. But we've also been joined by Eleni as well. So Hrutvik did his work on compiler verification, KML work, and Eleni worked on persistent memory systems. So specifications, big specifications. As many people know, ARM designs CPUs and sells IP. And yeah, we produce lots of specifications, and some of them are quite big, as has been mentioned. We've got the Architecture Reference Manual. I think the figure of 14,000 pages was mentioned before, but actually it seems to be closer to 15,000 pages. So I think that's probably a moderately large specification. But actually, it's not the only specification as well. I mean, there's other important parts of architecture that need to be specified. So I've listed a few here. We got the GIC, so that's another close to 1,000 pages. You got Systems MMU, nearly 400 pages there. And there's an assortment of random other specification documents. You know, this is a relatively short list of all the documents that ARM produces. So, I mean, they vary in size considerably. Obviously, the big one that most people refer to when they're talking about ARM is the A-profile architecture specification. And part of the reason for the size of it is really that it's covering two instruction sets. So you've got the legacy 32-bit architecture as well as the 64-bit architecture. But as the talk goes on, there may be some hints as to other reasons for it being relatively large. I mean, it's covering a lot of material to do with not just the instructions, but the memory model, virtual memory, various features, extensions, details about registers and things like that. So it's packed full of content, not just to do with simple, what does an instruction do? The documents themselves, it's mostly prose. There's a fair amount of tables and diagrams, and of course the pseudocode that a lot of people are familiar with. But actually, I mean, some of these documents are relatively light on pseudocode. They are mostly still prose and tables, diagrams. And a reasonable amount of the content actually is produced from data. I mean, it's coming from databases. I mean, the content itself is generated. And actually, talking about sort of big specifications, I mean, one of the significant challenges is actually producing a 15,000-page document. I mean, it's let alone actually doing any verification work. That's a relatively large document to be able to reliably generate. And there's a lot of engineering effort that just goes in terms of that and managing all of these databases and making sure everything's working properly. So as well as there being all these databases which help generate content, there is actual sort of more formal specifications that are used to generate content as well. So the instruction set. So the instruction semantics descriptions are often actually coming from ASL, but there's other parts, and I'll get onto that later, that are also generated as well. But the prose does vary. Some of it is just sort of open prose, just descriptive prose, but actually the more technical sections make use of something which we call rules-based writing. So the basic idea there is that sections of the document are tagged with a label, and the label will give some sort of indication of some sort of category. The important ones being mostly declarations and rules, and some of it is just additional information or background as to usage of a certain feature. And these things are then identified with a unique tag so that if someone is then commenting on the architecture or in discussing the architecture, you can uniquely identify where it lies within a document. So this is quite a useful feature. And I give an example of that here. I sort of semi-randomly just picked a page out of the ARM to give a flavor of what it sort of looks like. I mean, we have a nice diagram here, and rather entertainingly, it's called a counter example, but this is an example about counters rather than a counter example. But we do see our rules here. So we've got this unique tag, and then if you're wanting to refer to this bit of text, if you've identified that there's some issue with it or something, or if you're trying to understand the architecture, you're designing your CPU and you're wanting to talk to the architect about some particular requirement, you can say, well, I'm not too sure about WP, WQD or something like that. So this is sort of a very useful feature. And this one comes from one of these extensions. So, I mean, this large document is split off into chapters, and some of the chapters might just be covering an extension to the architecture. This has come out of one of those sections. And this is the embedded trace extension section. And I guess a key point to be making here is that actually the rules are more general than the ASL. So they're using prose, so it can be more expressive. And they still are important. So in order to be a proper ARM implementation, you must follow the rules. It's not just a case of, just do what the pseudocode says. You've got to follow, you've got to pay attention during those 15,000 pages and not miss any of these rules, or otherwise you've gone wrong somewhere along the lines. And talking about the pseudocode, there's also a section in the documentation, getting quite towards the end here, down to appendices, I think we're section K here. It starts actually talking a little bit about the limitations of the pseudocode itself, and you sort of have to pay attention to this as well. So there's some general limitations of the pseudocode, and often this is to do with undefined behavior, exactly what the code means in the presence of undefined behavior, and there's sort of different categories of these. So you've got implementation defined and unpredictable and undefined. So here, the pseudocode could be considered misleading. So you've got to carefully figure out what's going on in the case that you've got an unpredictable. So very careful interpretation of the pseudocode is needed at that point. And the same is also true in particular instructions as well, in particular to do with ordering and memories, which obviously Peter is super aware of. So the key point is you shouldn't put too much significance on the order in which memory access is occurring within the pseudocode itself. Again, things to do with undefined behavior and how it all fits in. And there's also details to do with timing of things like, when an exception occurs as well. If you're part way through running an instruction, what exactly happens if an interrupt occurs in between? The pseudocode doesn't really fully capture everything there, which is, this is a limitation of the specification language itself. So you sort of have to be aware of these things. And this is where this rules-based writing comes in, because if there's a discrepancy, it's usually what's written down in the rule that takes priority. It's not the pseudocode. I'll very briefly say something about CPU verification at ARM. This isn't really what the talk's going to be about, but in general, this happens as part of the central engineering group. And for the most part, they're using standard EDA tooling, Cadence Jasper. Alistair Reed in the audience here helps develop an approach which is still used at ARM, this isoformal approach, which is based on using the ASL specs as a reference for what instructions should be doing. But I'll move on to talk about specification and verification within my particular group. So this is within the architecture and technology group. So Jad sort of leads up that group. And there's two primary focuses here. One is what a lot of people will be familiar with, on to do with the memory model. And the cat and herd tooling, toolchain is used there. And that's very directly connected to the documentation now. So that work contributes to various sections within the documentation, but I've highlighted two particular ones. One is section B2, application level memory model, and there's also the virtual memory system architecture. And notably, the English text for this section B2 is now automatically generated from the cat file. So there's a sort of a formal description of what it is, and then that gets translated into a verbal description that sort of, so this is provides reassurance that something hasn't gone wrong when you're sort of manually translating it into language. So if you're editing the original cat file, that gets then reflected in the documentation itself. There's also work in this space to do with actually, checking CPUs actually conform with the memory model as it's formalized. Another thread of activity, quite active at the moment, is to do with standardization and formalization of the specification language, ASL, so the domain specific language. And documents relating to that are sort of public now, so you can get hold of them from developer.arm. And there's 4 key documents there. So we've got a language typing reference, a semantics reference, syntax reference, and there's also a document telling you about how much progress is being made and what's left to be done. So a lot of this is in sort of an alpha stage, so it's still work in progress, but this is out there for early access. So moving on sort of closer to my own work, we have been using theorem-proving within ARM, and I present here 2 bits of work that I've been involved in. We had hoped that Hrutvik would actually talk about another major thread to do with actually trying to use theorem-proving for this ASL formalization work, but we haven't been able to achieve that as part of this talk. Hopefully in the future there'll be probably a separate talk entirely about that, so watch out for that. The 2 threads I will talk about though is some RMM verification work, and Elaine's been involved in that, and also some work on something called feature constraint verification. I'll explain that when I get to it. So the first one, RMM specification and verification. First of all, I should explain, well, what is an RMM? So actually earlier in the week, we had a diagram that looked quite similar to this, except it missed out. It just contained this yellow bit in the middle. So we had PKVM as your hypervisor, exception level 2, managing virtual machines at sort of EL1, and for losses, and then applications at EL0 as user code. But actually, we have a level below that or above it, whichever direction you want to view it. So you actually have monitor code, which is enabled to actually partition the architecture actually into multiple worlds. So people will be familiar with this world, the trust zone world, effectively, and that's been around for quite some time now. But more recently, there's been the ARM confidential compute architecture, which is providing another world for enabling confidential compute workloads. I mean, particularly you'd be talking about cloud scenarios here, but doesn't have to be. I mean, it could still be on your phone just doing this sort of stuff. So what does ARM CCA provide? Well, it provides protected execution environments that offer confidentiality and integrity of user data. In particular, if you're paranoid about whether or not you can trust the hypervisor. So if you're doing some workload in a cloud, but you don't trust or you don't fully trust the cloud provider, you don't want them to actually have a look at all of your secret data, you would use this technology to ensure that they're not able to snoop on your data directly. So the hardware itself and the RMM software provide confidentiality and integrity guarantees. Availability is not assured, so the hypervisor could just shut you down and say, well, you can't run your job. So I should probably go back to this one. I've added in a couple of arrows, and these are sort of highlighting interfaces. So we've got this bit of firmware running in Realm exception level 2. So this is sort of at the same level as the hypervisor, but it's not a full hypervisor. It's just providing services to the full hypervisor. And we've got two interfaces. There's one for the realms to talk to it, but the key one is this RMI one, where the hypervisor actually interacts with the RMM. ARM has helped contribute to a reference implementation of this code. But the critical thing is that ARM produces yet another specification. So this specification is 313 pages. And rather unusually, I mean, it does use rules-based writing, but it also uses preconditions and postconditions to describe the behavior of these RMM commands. So this is actually using ASL in a very different style. So this isn't giving an operational semantics, it's just giving assertions about the behavior of the commands. And one of the main jobs that the RM's got to do is page table management. This is stage 2 page table management. So this is mapping intermediate physical addresses to physical addresses. So this is isolating VMs essentially. And hypervisors such as KVM can talk to the RMM. The host hypervisor manages the resources in terms of the allocation of memory, but it's not able to actually access the contents of the memory itself. So being a sort of an axiomatic style in terms of pre and post condition specifications, this was actually sort of quite a good fit for doing verification work. And we had a paper 2023 on this. It covered two things. I mean, one was actually verification of the implementation using CBMC. But the actual spec itself was formalized in a whole, and we verified some invariants. So the initial verification covered 22 of these commands, which was the vast majority of the commands. And we tracked that specification as it was being developed, so right from the alpha stages through beta, right to the release versions. And unsurprisingly, most of the value in terms of identifying issues with the specs came at these early stages, alpha, beta, when details of the spec were just being thrashed out. But this work continues because, more commands get added, more features get added, as is the way with architecture. So we've got 27 new ones to handle now. These are things for doing like memory mapped I/O. And there's also a new feature called planes on its way. This formalization work started off with relatively modest aims, which was just to somehow validate the spec by just sort of essentially trying to run it using a bit of automation in whole. But this developed later on, eventually came up with some sort of operational version which we could verify. But the key bit was actually, the early successes in just doing this initial modeling, which flushed out a lot of initial issues with the spec, this then gave us the confidence to go on to do a proper invariant verification. The major challenge going forward is actually just sort of maintaining this formalization as these new commands keep on getting added. And making sure that we can still demonstrate that we're getting a return on the investment of the work here. The spec itself, is getting updated internally roughly on a monthly cadence. So actually trying to keep up with that in a theorem-proving setting is extremely challenging. And you do have to make very pragmatic choices and try not to do too much. And an interesting feature, it's mostly been just a one-person effort throughout that. And there's also been a handover, which is unusual for theorem-proving work as well. In that, I started off doing the formalization and the proofs, and I've handed over to Eleni, and she's had the unenviable job of actually trying to keep it going, and she's done brilliantly there. But I think in general it is a big challenge that possibly hasn't been mentioned too much about, handover of these big formalization efforts, getting new custodians for big projects and actually keeping them going, I think is a very significant challenge. I'm going to have to whiz through this one. Features and traits. What are features? Features are sort of optional bits of the architecture. And we were joined by Magnus on his sabbatical for 1 year and he worked on a validator for some of this data, which is used to generate the documentation. So this is the bit of the documentation that gets auto-generated, and this is telling us details about features, and it's got constraints on them. And unlike some other architectures, actually, might actually deprecate things, that if you actually implement this new feature, you cannot implement another feature. And it's also got constraints on things to do with ID registers as to what values they might be holding. I'm probably not going to have enough time to
get to the questions for a few minutes.
Okay. So actually maintaining this database became clear that this was a significant challenge. The main issue here is that actually, surprisingly, well, maybe not that surprisingly, there are actually hundreds of features, and there are actually quite a lot of architecture versions, actually. There's about, 20 plus architecture versions. By the time you get all the point versions and V8s and V9s and everything, and in development stuff, it ends up being quite a large number. So all of this is sort of these relationships between all the features and the versions and everything is captured in a database. But it was getting to the point where actually logical mistakes could creep in. So what could go wrong? Well, it could turn out that actually the entire lot was completely inconsistent. So it had a requirement that you required feature A, and oh, by the way, you can't have feature A as well. But it could also be that particular features could either, they're not optional in any way. They're either always set true or always set false. And again, that's regarded as a bad thing. So if you had feature A imply some ID register is greater than 2, but then you say, well, it also has to be less than 1 as well. That doesn't work. That basically means feature A has to be false. And obviously, this is a good fit for SAT SMT. And we used Hull actually as a programming environment for just sort of interfacing to SAT SMT solvers. And this slide's basically about the fact that actually we're mostly interested in unsat here. So we're wanting these constraints to actually be satisfiable. So normally you use SAT as a way of getting a counterexample. We're not actually interested in counterexamples. What we're interested in is essentially failed proofs. So we're wanting unsat cores. So if we've got, for example, feature A implies something and feature A implies that that's not true, we know that we can't have feature A, which is bad, but what we want to know is what are all of the constraints which mean that we can't have feature A? So we're basically minimizing the set of all constraints down to those that are problematic. So we use Z3 for this. It's very fast, but we do have to make a lot of calls, in particular when we're doing things like trying to figure out which features are actually semantically equivalent to one another or disjoint from one another. So the cross product, or half the cross product, is very large, so that means that you're making a considerable number of calls. And actually interfacing to this stuff is quite important as well. So this has to be extremely easy to integrate into CI flows, and that people can actually interpret the results. So we produce HTML and JSON output. And I think I've managed to whiz through right there. So I'll just leave the concluding marks up there.
Thanks so much.